Hello, can people hear me? Can you type if you can hear me? Oh, perfect. Okay. Good, good. Right, so welcome to the 6th webinar. So it's been, and today the 3rd physics assignment was published. Very sorry for the delay. We are trying to make it as good as possible. And there are not so many questions, so you should be able to complete them. And for those of you who are studying further maths and have done mechanics already, you will probably find this assignment easier for you because most of the stuff is done in the further maths mechanics course. Anyways, so without any further ado, let's, a spotlight. Yes, spotlight myself. I'll share my screen as normal, and we'll go through 8 questions today. And feel free to ask any questions. I'll try to answer them. I'll keep the chat open. Well, these topics are still covered in the physics course. It just will require some extra work for you if you're not doing mechanics for further maths. If you're doing mechanics or further, well, it's typical. I mean, people who study further mechanics find it easier to do the physics mechanics course, and vice versa, of course. So statistics can be challenging. I agree. Okay, and okay. Well, then you have something to. Then you'll complete some work now that you won't need. You won't need to spend so much time on it in year 13. So that's good news, of course. So I'll just show. Okay, so the chat is here. Okay. Right. So the first question is quite simple in a way because it's mostly covered in. I mean, I think I saw a year 8 question which went in a similar fashion. I just want to establish that we are all on the same grounds and we understand the same concepts. So what forces are acting on a car when it's accelerating from standstill? Well, in year 8, you would say it's the driving force, but really, there's no actual such thing as driving force. Some other object is pushing the car. So which object is pushing the car? Can somebody tell me? Which outside object is pushing the car? Yeah, the floor, of course, absolutely. If there's no floor, if the floor did not have any grip, the car would not be able to move forward. So that's the force. So I'm mostly drawing the forces acting on the car, but also I'm driving a force from the road onto the car. So let's have a look. So the car is attempting to spin its wheels. This is a front wheel drive car. So the front wheel drive attempt to push the ground to the left. If the ground is loose, the top layer will actually move to the left. If the ground is solid, the ground will stay put. But what would happen is that there is, according to Newton's third law, absolutely, Newton's third law, the ground will push the wheel forward with an equal and opposite force. Okay, so this is friction on road, but this is friction on friction on the car. In other words, the road is pushing the wheel forward. So it's a bit counterintuitive that the car is actually driven by friction. But when you think about it, well, it makes perfect sense. If there was no friction, the car wouldn't be able to move forward. And that's the first force on the car. Then it's accelerating from standstill, so we can neglect air resistance in this case. Then we draw the weight of the car. The weight of the car, the center of mass of a modern car is approximately here, and the weight of the car, which is usually much bigger than the friction force. So that is the weight of the car. Weight of the car, and there is normal reaction in the wheels, and normal reaction in the wheels, normal reaction here, and normal reaction here. Okay, why did I draw the second normal reaction bigger? Can somebody type in the chat? R2. Why is R2 is bigger than R1? Yeah, well, the engine, of course, the engine causes a shift in the center of mass. So the center of mass is approximately here. So it's closer to the center of mass. Therefore, the front reaction force is bigger. And if you look at a car manual, they say that you need to inflate the tires to a higher pressure in the front. And also, there's one more thing. There's also some friction when the car is attempting to roll. There is some resistance. There is some resistance to rolling, but this is quite a small force. So I'm going to try to draw it here. So resistive force. We can call it friction, resistive force, but I'm just going to generalize it. Resistive force. So this is the diagram, and I hope we understand we're on the same, that friction can go either way. Friction can go forwards or friction can go backwards. Sorry for my notifications. I was sure I switched them off. Anyways, the friction is the driving force for the car. That's very important. That's pretty much it. And as you can see, the forces on the car are unbalanced. Even though this force is equal and opposite to this force, these forces are applied to different objects. So we don't consider this force when we're talking about forces acting on the car. And if we look at the forces acting on the car, we see that there's an unbalanced force to the right, unbalanced. Overall, there is an unbalanced force to the right. You can also convince yourself by drawing a vector diagram. So let's start with the small green forces. Small green forces. So we have two green forces to the left, 1, 2. So these are those green forces. Then there's a red force upwards. There's a red force upwards. There's another red force upwards, R2. There's a blue force to the right. There's a blue force to the right. Well, I'm going to exaggerate it a little bit. Blue force to the right. And there is a blue force of weight downwards. The weight is downwards. So therefore, this is friction force, force of friction. Then there is R1, R2. Then there is the blue force. There's the friction, force of friction on the car, which is this one. And there's the weight of the car. And overall, you can see that there is a resultant force to the right. Overall, there's a resultant force to the right. It's the resistive force. Well, if you ever tried pushing a car by your hands, you feel that, well, the car is not easily going forward. There is some resistance to it. It's not a big force, but it's the resistance to rolling. This comes from the friction in the axles. This comes from the tires, tires being squashed by the weight of the car. So you need to deform the tires, if that makes sense. So the tires squish it in. You kind of need the force to. Well, so as the wheel rolls, a different part of the wheel has to be compressed, and this is that resistive force. So there are many small forces which I just put together and say it's a resistive force. It's the car resisting to rolling. Okay. Hope that makes some sort of sense. I think mostly it comes from the rubber of the tires, which doesn't particularly like being deformed as the car rolls. Okay, moving on. Somebody's unmuted. Can you please mute yourself? The tablecloth trick. What is the minimum acceleration of a tablecloth so it can slide under a glass placed on top? Friction with the table is negligible. Friction between the tablecloth and the glass has coefficient of 0.3. We talk in reasonable detail in the assignment about the friction force. But basically, the friction force goes like this. Oh, okay. If you're not familiar with the friction force, if you're not familiar with the equation, force of friction is equal to mu r. If you're not familiar with this equation, can you please type 0 in the chat? Okay, so I need to explain some things. Okay, so let's say you have a table. You have a table, and on top of that table, you have a block or a book. It doesn't really matter what it is. And let's look at the forces acting. Well, there's the weight and normal reaction force, of course. There's the weight, which is going downwards. And there's the normal reaction. We tend to draw forces where they are applied. So the weight is applied at the center of mass. So mg is the weight at the center of mass. Now, normal reaction force is applied at the center of the contact area, which would be here, which is not very comfortable. So we just tend to shift sideways a little bit and say there's a normal reaction force from the center of the surface. It's not actually the center, but it's close enough. And this is the normal reaction force. Sometimes we use N for normal reaction force. So if you see N, don't be surprised. Normal reaction force. And because they're not moving up or down, of course, R is equal to mg. That's the normal reaction force from the ground. Okay, now we attempt to push the block with force F, and well, there is obviously some friction force. There's some friction force, and let's write this down. friction is applied at the same point where the R is applied, because it's also due to the reaction of the surface. It's kind of surface sideways, so it's kind of sideways reaction, or in more scientific terms, it's the tangential reaction. Right. Okay. Tangential reaction. It's very rarely called tangential reaction. So this is the friction force. Okay. And from experience, when you're pushing a heavy object, you know that it won't move for quite a while until it reaches a certain value, until the pushing force reaches a certain value. So I will draw a graph of the friction force versus the pushing force. So this is the pushing force, and this is the friction force. Friction. So the pushing force is this, and this is the friction force. And while it is not moving, they have to be equal. So if the block is not moving, because these are the only two horizontal forces, they're not moving. So they have to be equal. Therefore, for some time, they will be equal. They will be equal until a threshold is reached. This is when the block starts to slide. So basically, I mean, simple example, just put your phone on the table, try to push it, and at some point it will start sliding. And the heavier it is, the more force you need to get it moving. And the maximum, and after that, when the object starts to slide, the friction force will be constant. Okay. And we call this static friction. Static friction. Friction. And we call this dynamic friction. Dynamic friction. It's a transition from stationary to sliding. When it's stationary, the two forces have to be equal. But then a friction force cannot be any bigger. So there's a maximum value of the friction force. And this value, as it turns out from experiment, this is purely experimental, it's equal to mu r. And of course, because this is also equal to mu r, this is mu r. And mu is the coefficient of friction. Mu is the coefficient of friction. Mu is the coefficient of friction. Usually mu is between 0 and 1. 0 and 1, usually. Because it can be more than 1, usually, and this is purely experimental. Usually from 0 to 1. So for example, so steel on ice, and you can look those coefficients up. Steel on ice. Okay, I don't want to get, because I don't know the actual value, but on ice, you could have a coefficient something like 0.1. On a road, you can have coefficient of friction 0.8. Yeah, something like that. So what does this mean? So let's say you have a block of 3 kilograms. 3 kilograms. For simplicity, we'll assume G is 10. So the weight of the block is 30. Coefficient of friction does not depend on the reaction force. The friction force depends on the reaction force. So for a 3 kilogram block, the weight is 30 newtons. And the normal reaction is 30 newtons. So ice, and let's call it tarmac. So on ice, the friction force mu r is equal to 0.1 times 30, which is 3 newtons. So this is the minimum force you need to get this block to move if it's sitting on ice. On tarmac, mu r is going to be 0.8 times, sorry, from the unneat handwriting, times 30, which is 24. If I'm any good at maths, 24. So 24, the maximum friction force can be 24. So if your pushing force is more than 24, then it will slide. If it's less than 24, it will remain stationary. Okay, hope that makes sense on ice. So let's look at the tablecloth. So we have a tablecloth. So I'll draw the tablecloth. Unitless, yeah, no units. And there's a glass on the tablecloth. There's glass on the tablecloth. Okay, so we are attempting to swiftly move the tablecloth to the left. So the tablecloth accelerates to the left. And there are two options. Either the glass accelerates with the tablecloth, or the glass slides off the tablecloth. Or the glass slides off. So let's look at the forces acting on the glass. And there's the weight. There's the weight. There's the normal reaction force. Okay. You can draw them from the center. Sometimes it's more convenient, but this kind of makes a little more sense because we are applying the force here. Normal reaction force. And which way is friction? Which way is friction on the glass? In the chat, can somebody reply? Which way is friction? So the glass is on top of the cloth. We are pulling the cloth to the left. The glass experiences friction. It's somewhat similar to the car. To the right. Okay. Right. Okay. To the right. Well, It is left. Yes, it is left, Matthew and George. Because if it was to the right, the glass would be accelerating to the right, but it's not. Well, it's in an ideal world, it will stay where it is, but actually it will move slightly to the left because of the tablecloth is moving to the left. So there's a friction force here because the tablecloth is attempting to slide left and it's kind of gripping the glass with it. So the friction force is to the left, force of friction. And we know that the maximum friction force is less than or equal to mu r. The friction force is always less than or equal to mu r. Okay, so friction, and then we can write. The glass will also be accelerating. The glass will also be accelerating. And let's call it A1. Or let's call it A0, and let's call this A. And then we write Newton's second law. Newton's second law says that mass acceleration is equal to the resultant force. And there's only one force, which is the force of friction, because R and mg are balanced. So these forces are balanced. So the only force to the left is F friction. So F friction. And we know that it's less than or equal to mu R. But R is also equal to mg. Okay, so we write down MA is less than or equal to mu mg. And a wonderful thing happens. The m cancels out because we're not given m, but it turns out we don't really need it. So acceleration is less than or equal to mu times g. So for simplicity, I will say g is 10 newtons per kilogram. So A is going to be less than 0.3 times 10, which is 3 meters per second squared. So the acceleration of the glass cannot exceed 3 meters per second squared. So if it's 3 meters per second squared, it will accelerate with the cloth. And if the cloth's acceleration is more than 3, then the glass won't keep up and will slide off. Okay, so let's put it down in words. Maximum friction force. Friction force is equal to 3 newtons. Maximum acceleration. Oh, sorry, what did I say? 3 newtons. 0.3 is 0.3 times mg, because we don't know m. Maximum acceleration is 3 meters per second squared. So if the cloth exceeds 3 meters per second squared, the glass will slide off. Okay. How much sense does that make on a scale of 1 to 10? Okay, that's good to hear. Okay, good. Yeah, just remember that friction force does not necessarily go against the motion. In this case, the glass is moving to the left and the friction force is also to the left. Just like with the car, the friction force is to the right and the car is moving to the right. So be very careful with this. Okay, a car manufacturer claims the car will go from 0 to 60 in 1.9 seconds. That's a true story. That's a true car manufacturer and a true car. The friction coefficient the friction coefficient between a tire and a dry road is typically 0.7. Is the manufacturer's claim justified? Well, let's see. Let's see. It's kind of the tablecloth trick again. The problem with really fast cars is that they have a lot of power, but you're always limited to the only thing that connects the car to the outside world is the tires. So your tires cannot deliver more than the maximum friction. And even though even if your engine is super powerful, you would not be able to transfer that power to the wheels if there's not enough grip. If that makes sense. So this is a little bit of an engineering question, but anyways, let's find the acceleration. So acceleration is, as you know very well by now, is the final velocity minus initial velocity divided by time. Time and a quick conversion from miles per hour to meters per second. What am I doing? 60 divided by 2.24, about 27 meters per second. I don't need to be too accurate. 27 minus 0, the initial velocity is 0, and the time is 1.9 seconds. So the manufacturers claim that the acceleration of the car, 27 divided by 1.9, is 14.2 meters per second squared. Now, as a physicist, you should really say, like, really more than acceleration of due to free fall. So if the car is in free fall, so the car will accelerate along the road faster than it would accelerate in free fall. And but then you consider this, and this is a real value. This is from research. So let's find the maximum acceleration. So we know that the force of friction, the maximum friction force is equal to mu r. So, and r is equal to mg, so it's equal to mu mg. And we know Newton's second law, so mass acceleration is equal to mass acceleration max is equal to mu mg. Therefore, mass cancels out. Maximum acceleration maximum value for acceleration is mu g, which is 0.3. For simplicity, again, I will say 10. So 0.7. 0.7 times 10, which is 7 meters per second squared. Second minus 2. So we have a discrepancy of at least 2 times. So it will. The car is, so with this acceleration, 0 to 60 would take time realistic. from 0 to 60 would be equal to 27, the final velocity divided by the acceleration, which is 7. So realistically, on a real road, no car can go from 0 to 60 in faster than in 3.9 seconds. 3.9 seconds. Right. You can increase you can increase the friction coefficient by using very hot tires and a perfectly smooth surface, and of course there's a downforce on the car, but it's ideal conditions in a vacuum, right? A real car, a car on a real road would not be able to accelerate that fast, even if it has all the horsepower in the world. So yeah, so that's a more realistic value for any car. So don't believe any claim you see. Okay. So what would happen actually? The wheels would just keep spinning. The wheels would spin and the car would not go forward because there's not enough grip. Okay, right. Now getting into real stuff, like real difficult stuff here. How to work with Newton's second law. Newton's second law seems very simple, and actually it is once you understand how to use it. If you want to use Newton's second law, what you need to do is draw a free body diagram. You draw the body and the forces acting on that body. And then you write down Newton's second law. Newton's second law sounds like this. Force, mass times acceleration is equal to the sum of forces acting on that object. So that's Newton's second law. So quite elegant in a way, but let's consider the three objects here. So we need to draw them separately. So let's do that. And it is important that you draw them separately. So the first one is very easy. So there are only two forces acting on this object, and this is the tension force. We all call this tension 1. Tension 1, because there are two ropes, one rope and another rope, so tension force. And there's the weight, the gravitational force, mg, m3g, m3g. And well, that's kind of a pickle. You don't know which way the system will accelerate. It can either slide to the right or it can slide to the left. From the looks of it, I'll do my best guess. My best guess is that this, because this is 4 and is directly down, it will cause the masses to accelerate upwards. But this is just my guess. And I'm drawing this guess here on the diagram and say acceleration. Acceleration is downwards. If I get a negative result for acceleration, that means my guess was incorrect. And that's easy to change. Yeah. So that my guess is that the acceleration is downwards. Okay. Let's draw the second object. Let's draw the second object. And don't need that. Now, when you're doing this, it is important to describe the frame of reference in which you are working. So I'm going to draw a coordinate axis here. This is the x-axis, and this is the y-axis. I've shown you this approach previously. This is a fantastic instrument because now you can project your forces onto these axes. So on M2, there are several forces acting. So of course there's the downwards force, which is M2G. There is the tension force from the first rope. The first rope is pulling the mass up the slope. That's tension 1. There is the tension 2. The other rope is attempting to pull it down the slope. And there's the normal reaction force. The normal reaction force from the surface, it's called normal because it's 90 degrees. So we draw it like this. So this is the normal reaction force. Okay, let's call it R. R2. And here, because we need to project either on the x-axis or on the y-axis. The x-axis or the y-axis. So I'm going to split the weight into two components. One component perpendicular to the slope, so along the y-axis, and one component parallel to the slope, which is the axis. So after looking at the triangles, you will understand that this is 30 degrees. 30 degrees. There's several ways to do that. Please convince yourself that this is in fact 30 degrees. The easiest way to convince yourself that this is 30 degrees is to think what would happen if this angle were to get smaller. So as this angle gets smaller, this angle will also get smaller. So when this is 30, this is also 30. I don't want to go too deep into explaining why this angle is 30, but please do convince this is done through similar triangles. Similar triangles. So therefore, because we know already how to split them into components, we say that this is M2G cos 30, or cos theta for now, it's fine. And this is M2G sine theta. Okay, and then we draw the third block. And the third block is quite similar. Oh, no, not what I meant. Let's see. The third block. We just draw the forces. So we are just doing the diagram. And so this is M1G. This is R1. There's no friction, so there's only the tension force acting up the slope. Tension up the slope. Tension 2. Tension 2. And once again, so this is R1. This is M1G. Once again, I split the mg into components. I split it into two components, one along the x-axis and one along the y-axis. Because the axes, remember, the axes are like that. So this is M1G sine theta. and this is m1g cos theta. Okay, and now we just need to do one more thing. Write down Newton's second law. Now we will write Newton's second law in two directions, in the x direction and in the y direction. Now for the first object, the x direction doesn't make any sense because there's no forces in the x direction, horizontal forces. For this object, we of course use the normal, so x and y, like this, x and y, x and y. So there's no forces in the x direction, so it doesn't make sense. So Newton's second law. Newton's second law in the y direction only for this one. So it's m3a is equal to the sum of forces. M3a is equal to the sum of forces. And there are only two forces. And we assumed that because it's accelerating downwards, that this force is bigger. So M3a is equal to M3g minus T1. So mass acceleration is equal to the sum of forces. So MA, I remind you, is the sum of forces. Okay, how much sense does this make on a scale of 0 to 10? Okay, so you're all familiar with this. Good. The mass, well, not too many answers. Guys, especially if it's less than 5, please let me know. Because if you don't understand, I can, okay. 5. Okay. Right, so Newton's second law is that mass times acceleration is equal to the sum of forces. There are two forces acting on this block, M3g and T1. So we write down mass acceleration. Once again, mass acceleration is equal to the sum of forces. And there are only two. So mass acceleration is equal to M3g minus T1. M3g is in the same direction as the acceleration. So that's why it's positive. And T1 is negative because it's in the opposite direction. Does it make more sense now, Jakob? Or is there something else you are right? Okay. Well, we've written the equation M3a equals M3g. Then we take the second one, and remember we've changed the direction of the x and y coordinate, of the x and y. So x goes this way, and y goes this way. Y goes this way. So we have in the y direction, the easier one. So we have mass acceleration m2a y, the vertical acceleration, is equal to r2 minus m2g cos theta. Sorry, it's a r2 minus m2g cos theta. But there's no acceleration in the y direction. So this has to be equal to 0. There's no acceleration. Therefore, R2 is equal to m2g cos theta. We might not need it, but we might need it. So we'll just leave it for now. In the x direction, we've assumed that the object accelerates up the slope, and because the rope is inextensible, the acceleration has to be the same. The acceleration of M3 and M2 has to be the same. So we use the same letter for A. This is called a kinematic constraint. And we write down that M2A mass acceleration is the sum of forces. So it's equal to T1 because it's up the slope. And down the slope, we have two forces, T2 minus T2, and minus this green force, minus M2 G sine theta. This is the third equation that we might need to use. Now for the third block, in a very similar way, y, in the y direction, we have R1 is equal to M1G cos theta. Now they have to be equal because it's not moving in the y direction. And x in the x direction is M1A. R1 is equal to M1G cos theta. So M1A is equal to T2 minus M1G sine theta. So we have two more equations. It's a lot of equations, but this is good news. This is where physics stops. This is the end of physics for this question. Because all you need to do now is to find the you need to find A, and you need to find A, T1 and T2. Well, you just need to combine those two. And after looking at these two equations, the y equations, you will see that they don't contain A and they don't contain T, so they're kind of useless. So in this particular question, you won't use them. In the next question, you would. I probably won't have time to do that. I'll probably skip question 5, but you have 3 equations and you have 3 unknowns. I say that's a perfect combination. You just solve the 3 equations. They might look very horrible, but they're not. And now let me convince you that they're not horrible at all. So M3A is equal to M3G minus T1. I'm just going to write them out again. M2A equals T1 minus T2 minus M2 G sine theta. And the third equation is M1A equals T2 minus M1 G sine theta. Now, if you're really uncomfortable with letters, you can substitute at this point, because you know M1, you know M2, you know M3, and you know G. But let me do it without substitution, and this is the way you should be aiming to do those. Ideally, you should be substituting in the last moment. Before that, you shouldn't be substituting. So from the third equation, I get T2 is equal to M1A plus M1G sine theta. Okay. From the first equation, I get T1 equals M3G minus M3A. And I just substitute it into the second one. I substitute that into this one. And I solve for A. I hope that makes sense, especially for those rewatching that. So M2A equals T1, which is M3G minus M3A minus T2 is M1A plus minus M1G sine theta minus M2G sine theta. Take everything containing M to the left, and incidentally, you get M1 plus M2 plus M3 times A equals, now everything without, so it's M3G, M3G minus M2G sine theta minus M2G sine theta. Oh, and finally, A is equal to fraction M3G minus M2G sine theta minus it doesn't make any sense, M1. Apologies, M1. So this is M1 G sine theta M2 G sine theta all over M1 plus M2 plus M3. And once you got the final answer, then feel free to substitute. And so why is this beautiful? Because you can see that the units are correct. The units are definitely correct because it's M times G. We know G is meters per second squared. So therefore, dividing by M, we see a consistency with units. And this is a good indicator that we've done something right. So we substitute M3 is 4. So 4 times G. For simplicity, I'm going to use, I'm going to do it in terms of G. Minus M1. M1 is 3 kilograms. So 3 times G times sine 30 is 0.5. Minus M2, which is 1 kilogram, multiplied by G, multiplied by 0.5, because sine 30 is 0.5. And we have 4 plus 3 plus 1, which is 3 plus 1 plus 4, which is 8. So the answer is going to be 4g minus 1.5g minus 2. So 2g divided by 8, which is 0.25 g, which is approximately, okay, 0.25 times 9.81, which is 2.45 meters per second squared. Right, so that's the acceleration of the system, because all three blocks have the same acceleration. And to find tension, you just simply substitute that. So to find tension, I'll just do that. Tension in the first rope is equal to M3, which is what is M3? M3 is 4. 4 times 9.81 minus 4 times 2.45, which is equal to 9.81 minus answer. Sorry. 9.4 times 4 times 9.81 minus 4 times 29.4 newtons, and this one is M1, and so M1 is 3 kilograms times 2.45 plus M1, which is 3 times 9.81 times sine theta, which is 0.5, which is equal to 3.5 times 2.45 plus 3 times 9.81 times 0.5, 23.17 newtons. So the tension in the second rope is smaller. You can leave it as G, or 9.81. Okay. Using, okay, for our assignments, using GS10 is not a big deal. Okay, we won't take marks off you for using GS10. Okay. In A levels, you would lose marks if they. So I would, if I were you, I'd just stick to 9.81. By the way, in maths, they ask you to use 9.8, which makes life even better. So in A-level maths, you need to use 9.1, 9.8. So just to be safe, always look at on the exam paper what they're expecting. Right. So T1 and T2. So yeah, I mean, this the most complicated thing that you see here is the maths bit. Well, actually, it's not that complicated. You just need to be very careful not to make mistakes. But the physics is just that. It's just this bit is physics. If you get the physics right, if you get the physics bit right, that means this is physics. And physics, to do the physics correctly, you always start from a diagram. Without a diagram, it's almost impossible to get the answer. Okay, so moving on. Now this, I'll show you some things here. So it's a very similar problem, but now we have friction on the slope as well. So M1 is frictionless, M2 has friction 0.3. So for M1, the forces will be the same. The forces will be the same, so there's mg, there's the reaction force, there's the tension force. Note that I'm drawing them from one point. You can do that. This is allowed, just in different situations. One way is more convenient than the other. And for this block, we have the weight. We have the weight. We have the normal reaction. We have the tension. We have the other tension, and we also have friction. And for this block, it's the same. There's the normal reaction, sorry, the weight and the tension. So I'll just label the forces. So this is M3G. This is tension 1. This is tension 1. This is tension. This is tension 2. Sorry, tension 2. This is tension 2. They are the same, so I do apologize. The tension 2 and tension 2 are all obviously the same. There's R1, R2, R1, M1G, and M2G. And here we just have the extra force, which is mu R2. And when you write down the equation for the y coordinate, it's going to be R2 is equal to M2G. So for M2 block, for the M2 block, the y is going to be R2 M2 equal M2G cos theta. But for the x is going to be M2A, is assuming it goes upwards, it's going to be T1 minus T2 minus M2G sine theta, just like we had, and the extra force, which is mu R. But mu R, we know that mu R2, we know that R2 is this thing. So that's where we need that equation. So it's going to be M2A equals T1 minus T2 minus M2G sine theta minus mu M2G cos theta. Okay. I know these look scary, but do get used to them. This will help you a lot if you get used to those. Look, for example, so yeah, sorry. Let me finish with this. So this is the equation for the x value, and this is for the y, and this is for the x for block 2. I'm not doing block 3 or block 1 and block 3 now, but please do finish this. So this is unfinished. Please finish yourself. So a simple example, for instance, you have a block sliding down a ramp. A block sliding down a ramp, and what are the forces acting, or what is the acceleration of the block? Well, you draw the forces. So this is mg. There's the friction force, mu r. If it's sliding, then it's mu r. And there's the r. And we need to find the acceleration. Just for those who are going to rewatch, find the acceleration of the block down the ramp, and we say, okay, this is going to be the x-axis. It's sliding down. This is the x-axis. This is the y-axis. And we write down for the x-axis. We split this into components. And this is theta. So theta is the angle of the ramp. So for the x coordinate, and this is the y coordinate, this is mg sine theta. This is mg cos theta. So for the x coordinate, mass times acceleration is equal to the sum of forces. So mass acceleration is equal to mg sine theta minus mu r. For the y coordinate, for max, may is the sum of forces. So may is equal to the forces upwards, so r, minus mg cos theta. But this is equal to 0 because it's not accelerating in the y direction. So it's not accelerating in the y direction, so this is 0. So therefore, from this equation, we get r is equal to mg cos theta. And so from here, we get ma. We don't need to ax. We don't need to write ax because it's obvious. It's accelerating along the x-axis. We're not considering any other acceleration, so we can drop the x here. So it's mg sine theta minus mu r, and r mu mg cos theta. And we have m cancels. So acceleration of a block down the slope does not depend on the mass. It depends on the angle and the coefficient of friction, cos theta. This is a very important result. This is an acceleration of an object sliding down a slope. And this should be very familiar to you. And also, What is the condition that the acceleration is 0? So constant speed, for constant speed, we have acceleration is 0. So that means that sine theta minus mu cos theta is 0. So sine theta equals mu cos theta. And divided by cos, it's going to be tan theta equals mu. Right. So this is this is for constant speed. So this is constant speed. Now another result is that if mu is less than tangent theta, then we have acceleration. And if mu is greater than tangent theta, then the object won't slide. Object won't slide. So a very easy way to find the coefficient of friction is to put something on the block and turn it and angle it until it starts sliding. So once again, very carefully, I tilt it until it starts sliding. And the moment it starts sliding, tangent of this angle is equal to the coefficient of friction between the two surfaces. So this is quite a neat way of finding the coefficient of friction experimentally. So at the moment of sliding, so this is how you can measure coefficient of friction. Okay, so that's that. Now, okay, these are very simple. Okay, question 6 is much simpler. So let's do question 6. So two blocks are placed on a smooth table. The coefficient of friction between the two blocks is 0.4. Find the acceleration of the bottom block. Well, okay. So we place one on top of the other and push the top one. The bottom one would accelerate because of the friction force. So let's draw the forces acting on the top block. On the top block and on the bottom block. So the top block, we have the forces, we have the weight, which is M. Okay, mg. Then we have the normal reaction force, which is R. Now we are pushing it, so there's a pushing force F. And of course, there's a friction force, which force of friction. Okay, so then for the second block, there's the weight, so M capital G. Then there's the normal reaction force. But also the top block. So if the bottom block pushes the top block up, according to Newton's third law, the top block pushes the bottom block down. So there's, let's call this R1, and this is R2. R1 is also pushing on the top block. So if something is on, if the top block is on top, then it's pushing on the bottom block with a force equal to R1, equal to the reaction force. Okay, and then there's this friction force. So this friction, the Newton's third law pair, because if the bottom block exerts a frictional force on the top block exerts a frictional force on the bottom block. Friction force. So actually we can see that there are two pairs of two Newton third law pairs present in this diagram. This one. Sorry, this is R2 and this is R1. These are Newton's third law pairs. Okay, that's not good. And we just write down Newton's second law. So MA is equal to F minus F friction. And of course, R1 is equal to mg, so we don't really need to consider that. Okay, R1 is equal to mg. Just for the sake of it, I'll write it down. For this one, Ma is equal to F friction. Cool. Now, we know that the friction has a maximum value. We know how the friction has a maximum value. And the maximum value of friction is equal to mu r. So F friction maximum is equal to mu r. Mu r1 in this case. And r1 is mg. So let's do some numbers. So this is well, for simplicity, I'm going to use G is 10. G is 10. So this is 10 newtons. 10 newtons. So mu r1, that's equal to 0.4 times 10, which is 4 newtons. So the friction force cannot exceed 4 newtons. If it tries to exceed 4 newtons, it will slip. Okay. So let's assume that the F is 2 newtons. So first F is 2 newtons. So if this is 2 and this is 4, that wouldn't make any sense because acceleration would be negative. Acceleration would be to the left. Now, if you push something to the right, it doesn't go left. So therefore, it's not slipping. It's not slipping. And we can just solve it normally. So we can say MA equals F minus F friction. And we know that F friction is MA. So MA is equal to, so this is question A. No slipping. No slipping. MA is equal to force minus 2 minus MA. So A m plus m is equal to 2. So acceleration is equal to 2 divided by sum of masses, which is, what's the mass? 1 and 3. 1 plus 3. So that's 0.5. 0.5 meters per second squared. Half a meter per second squared, that's the acceleration of both blocks, because they're both accelerating to the right. Now, when the force is 40, it means it will be slipping. It will be slipping, and the friction force is equal to the maximum friction force. So so here we'd use different A's. So we'll have MA1 is equal to F minus F friction, and MA2 is equal to F friction. But we know that the maximum friction force is equal to 4, and because we are pushing with 40, it's going to slip, because there's no way the two accelerations can be equal. You can check that. The two accelerations cannot be equal, therefore there is slipping. And if there is slipping, there it is 4 newtons. So this is 4 newtons. Therefore, M1A is equal to 40 minus 4, which is 36. So small a is equal to 36 divided by 1, 36 meters per second squared. 36 meters per second squared. And A1 and A2 is going to be 4 divided by 3, which is 1.3 meters per second squared. Okay. Basically, what I'm saying is the bottom block cannot accelerate faster than 1.3 meters per second squared, because that's the biggest value of friction. Sorry, the friction, the limiting factor is the friction. If you push too hard, it still won't accelerate. I hope that makes kind of sense. I think I've overcomplicated things here. You can also do a very simple thing. Okay, why don't we consider the two blocks as one? This is one block of 4 kilograms. 4 kilograms. And well, there's a force of 2 newtons. So acceleration is going to be 0.5. I hope you're all really comfortable with this, meters per second squared. And if the force is 4 kilograms and it's 40 newtons, then it's supposed to be 10 meters per second squared. But that would imply that the friction force between them is more than the maximum. So this is not possible. So we cannot treat them as a single object when we are doing that. And this is the simple test. So it must be slipping. Must be slipping. So we cannot consider them as one object. And this one, this is a very important one. Yeah, guys, we're going to go over a little bit. This is a very important question, because there's a question somewhat similar to that. And there's a few things that are really hard to grasp here. So we have an inclined plane, 30 degrees. There's the inclined plane itself can move on the table, and it has a mass of m capital. And we have this block. And what is the force that needs to be applied to m so that the block is stationary? So there's no friction. We just push the bottom block to the right so that this block stays at constant height. So it will constantly be accelerating. So we draw the forces. We take the bottom one and we draw the forces. We have the friction, the force. We have the normal reaction force from the ground. I'll call it R1. This is F. This is the force mg, m capital G. And also there is this block. This block is pushing that way. This block is pushing that way, and this is force R2. This is the reaction force from this block. Now for the block itself, for the top block, we have the weight. So this is m small g. And there's the normal reaction force, and that's it. This is the normal reaction R2. And we know that vertically it is not moving. So here it is more convenient to split the R into components. Split the R into components. And this is going to be R2 cos theta. And this is going to be R2 sine theta. We know that they are both accelerating. They're both accelerating with acceleration A. Then, and looking at this, we can write down that MA is equal to R2 sine theta. That's the only horizontal force. That's the only horizontal force that is accelerating. It's mass acceleration equals horizontal force. And here, we don't need to consider the vertical forces again because they're balanced. It's not moving up or down, so it's only moving to the left. So we split this. So this is going to be so mass acceleration is equal to the F, horizontal force, and then to the left minus R2 sine theta. Okay, so from here we get acceleration. You have to have the same acceleration. Oh no, we do need the vertical forces. Sorry, we do need the vertical forces here, and this is so this is in the x direction, and in the y direction, it's going to be R2 cos theta is equal to mg. Yeah, that's important. So from here, R2 is equal to mg divided by cos theta. Okay, so we are plugging this into here. MA is equal to mg sine theta divided by cos theta. M cancels. So acceleration is equal to g sine theta cos theta. Or in other words, acceleration is g tan theta. G tan theta. And we can now substitute this into here instead of the second one. So it's going to be MA capital equals F minus MA minus MA. So from here, F is equal to M plus M A M plus MA, and so F is equal to M plus M G tan theta. And this is the answer. Sorry for rushing this question a little bit, but the important thing here is that they're both accelerating with the same acceleration because they are stationary relative to each other. The block is not sliding down. They have the same acceleration. But then all you need to do is just draw the diagram. Just draw the diagram and figure out the horizontal and vertical forces. And once you've done the physics, you just do the maths. You just solve the simultaneous equations. And one more question here. Find the tension in Europe. We won't have anything like that. We won't have anything like that on the assignment. But here, I just wanted to talk about kinematic constraints, which are mentioned in the assignment. So there's one thing you need to realize here, if this block is accelerating downwards with acceleration A, this block will be accelerating upwards with acceleration A over 2. Just because if this block moves a distance x, this will move a distance of x over 2. And then it becomes super easy to solve. So for M1, you do M1A is equal to so there's the weight minus the tension. So M1G minus the tension. And for M2, you write down M2A over 2, acceleration over 2, equals, so there are two tension forces, tension here and tension here. Well, can you move it mentally? Well, I mean, there is an explanation for that, but if you mentally move the first block by a distance of 10 centimeters, this block will move up by only 5 centimeters. Oh, this is not good. Right. Okay, I've got a slight problem here. If you move, will that work? All right, my touchpad stopped working and my mouse. Very sorry about that. They connect. Okay. Well, not exactly. The second block is not connected to the same string. It's connected to the center of the pulley. And the pulley itself moves, and it moves slower than the first block. This is called a moving pulley. So if the bottom block moves down by 10 centimeters, the the block, the block on the right moves up only by 5 centimeters. And that is why we have MA/2 is equal to, I haven't finished, but it just stopped working. I'm very sorry. I will write it down. I won't write it down. So it's going to be T plus T minus M2G. So I can't even type in the chat. Technology completely failed me. Anyways, I'll write it down. It's going to be M2A/2 equals T plus T minus M2G. And all you need is just to solve for a T. Solve for T and for A. You have two equations, two unknowns. And that's it. All right, I will fix that. Oh, that is the case where we didn't guess the acceleration correctly. Now it weighs, just not weighs more, it weighs more than double. More than double. The acceleration will be negative, indicating that your answer is not, your initial guess was incorrect. But you would get a negative answer, and it would be a valid answer. So you can still solve it like that. Okay. All right. So that's the end of the webinar. Thank you for coming. Thank you for your attention. Good luck on the assignment. And we've made it not that big, so you can tackle it in the remaining 2 weeks. You're welcome. See you. See you. Yeah, do email me. I'll try to answer. I'll try to answer.